everyone. This video is going to be an editorial for this past Codeforces Round 764 Div 3. So let's just get into it. Problem A. Let's just label this A. So we're given an array, and in some operation we can choose some indices of the array and increase all their values by 1. So we can choose like indexes 1, 2, and 4, increase them all by 1. This becomes 5, 3, this stays the same. This increases, and this stays the same. So this is one move. And we want the minimum number of moves such that all elements of the array are equal to each other. So I guess the first thing to notice is we can lower bound the answer by the number of moves it takes to get the smallest number. In this case it's 1 to the largest number. So the least number of moves that you take is the difference between these two. And that's because in each move you can only increase a value by 1. So for all of them to be equal, 4 can never decrease here. So for all of them to be equal at some point, they all have to be at least 4, which means that 1 has to move 3 times to get 4. And actually 6 is the largest number in this array, so we can lower bound the answer by 6 minus 1. And so our answer is greater than or equal to 5. And also, to show that it's possible with 5, we can actually just do a sequence of operations to make this whole array 6, 6, 6, 6, 6. So where they're all equal to the max number. And this is not hard at all. All we have to do is just keep choosing all the indices for a given move. Keep choosing all the indices such that their values are not yet 6. So in this case we would choose 1, 2, 3, and 5. So then the next one would become 5, 3, 2, 6, 3. And then we would again choose 1, 2, 3, 5. So obviously we don't have to output the construction or like the moves that it takes, but this shows that it's possible to have a sequence of moves that reaches this value of the max minus the min. So our answer is just the max of the array minus the min of the array. Yeah, and that's problem A. Okay. So now let's move on to problem B. This one. So we're given 3 positive integers, A, B, and C. Let's take a test case like 10, 5, and 30. And we want to choose one of these integers, multiply it by some value, and the resulting sequence should be an arithmetic progression. So in this case we could take the 5, multiply it by 4, and then the resulting sequence would be 10, 20, 30. And this is the arithmetic progression. So that's why the answer is yes for the first test case. So this problem, there's not much to it. We can simply just brute force I should label this problem B. So what we can do is consider whether the number we multiply is the first number, the second number, or the third number. So let's say it's the first number. We can calculate what this number should be based on these two values. So we can just do some computation and realize it has to be like 2 times 5 minus 30. 2 times the minimum, 2 times the average minus the maximum. I mean, we can see that if we let this value be x, we have x plus 5 minus x, which is the common difference, equals 30 minus 5. And that gives x equals this. So either the first value has to change to this number, and we can do something similar with the second value. So if the second number is the number that changes, we know what it has to change to. It has to be the middle of 10 and 30, which is 20. So it has to change to 20. And then we can do something similar with the last value. It has to change to 2 times 5 minus 10. So now if any of these three numbers is a multiple of their original number, so this, and that is, it has to be a positive multiple, because in the question it says m is a positive integer. So this is negative 20, but that is not a positive multiple of 10 because it's negative. This is 20, which is a positive multiple of 5. So that works. So if any of these three numbers satisfies that it's a positive multiple of their original number, then we're good. Then the answer is yes. And otherwise the answer is no. So that was pretty straightforward if we just brute force all three possibilities. Okay, problem C. In my opinion, this was pretty hard for problem C. But I don't know, maybe I just didn't, I don't know. But okay, so in this problem we're given a sequence 1, 8, 25, 2, and we want to turn this sequence into a permutation of 4 numbers. So some permutation of 1, 2, 3, 4. And the way we can change this array is take a given value and divide it by 2, taking the floor. So we can change like 8 to 4, and then we can change 25 to 12, and then we can change 12 to 6, then we can change 6 to 3, and that is our desired permutation. So we want to know whether, given an initial permutation, whether it is possible, given an initial array, whether it is possible to reach a permutation like that. So yeah, that's the problem. So I think this will help with visualizing this. So I'm going to draw like a diagram. So this is, I think it's called a heap. That should be enough. We'll just put 11 here. So notice how in every operation applying an operation to some number takes it to its parent. So 8 goes to 4, 9 goes to 4, 11 goes to 5, 6 goes to 3. This is just dividing by 2 and taking the floor. So our job is to make the numbers 1, 2, 3, and 4. So the way I did it was with a greedy approach. So what we do is we loop through the numbers, and if it's in the range from 1 to n and it's not already been used, then we leave it. Otherwise, we divide by 2. So for example, we first have the number 1. We just use 1 as it is. We leave it as it is. Then we have 8. 8 is not in the range from 1 to 4. So we divide by 2, and we get 4. 4 is in the range, and it's not been used yet, so we leave it at 4. So I guess the question with this approach is, could there be a solution, or could there be a time where it's better to put 4, instead of leaving this 8 at 4, maybe bringing it up to 2. So 1, 2. But I claim that it's always better to leave it as big as possible. And I guess sort of the intuition behind this is, notice that everything in 2's subtree can go to 2 if it wants. But everything in 4's subtree not only can go to 2, but also can go to 4. So if we have something in just 4's subtree, there's no reason to bring it all the way up to 2. We might as well just leave it at 4, and since anything that appears in this again can also be brought to 2 anyway, then we can just it makes more sense to just leave it at 4 and leave a more general set for later numbers. So I'm sure this can be rigorized with an exchange argument or something similar, but intuition's all you need for Codeforces. You don't need to prove things rigorously. So yeah, that's problem C. So I guess to summarize the algorithm, you just keep dividing by 2 until you reach something in the range from 1 to n and you haven't seen it before. And if the resulting thing is a permutation, or if something ends up continuously dividing by 2 and reaching 0, then it's not possible. Yeah. Okay, so that's it for problem C. Now problem D. Palindromes coloring. So this problem, I didn't think about it as deep as I should have in the contest. So if you're reading my solution or something, probably this will be more important, because I didn't even understand how my solution worked at the time I coded it. But yeah. So we're given a string bxy axz ay and 2 colors, or k colors, but in this case 2. So we want to color you don't necessarily have to color every letter. We want to color these such that everything in the same, everything that's in the same color. So if this is red, this is red, this is red, then all the red letters can be rearranged to become a palindrome. So this can become ABA, which is a palindrome. And let's say this is blue, this is blue, this is blue, and this is blue. Then XY can be rearranged to XYYX. So maybe like this is the red bucket, this is the blue bucket. AAB, XY, XY. So we want to color the letters such that it's possible to rearrange each color to make them palindromes, and we want to maximize the length of the shortest palindrome. So like we want to maximize the minimum size, the minimum number of letters corresponding to a color. So in this case it would be 3, because there are 3 letters here, 4 letters here, 3 is the minimum. I guess the problem statement seems a little complicated, but a lot of it just goes away, a lot of the complication. So the first thing to notice is that, or first of all, what we should identify what it takes for a given sequence of letters to be able to be rearranged into a palindrome. So if we have 2 of the same letter, AA, then that can obviously be rearranged into a palindrome if we just put one of the letters at the beginning, one of the letters at the end, since they correspond to each other. In fact, however many pairs of equal letters we put. So if we have AA, AA, BB, ZZ, we can rearrange these letters such that it's a palindrome just by simply like appending the pairs on either end. So given like sequence of any number of letters such that each letter appears an even number of times, that can be rearranged into a palindrome. And also, if there's at most one letter that appears an odd number of times, we can also do it. And the reason is we can just stick the odd one out in the middle. So let's say we have Y, Y, Y added to this. We put one Y here, we put one Y here, and we put one Y in the middle. If there's any more letter with an odd frequency, then we can't make a palindrome. So that is a big observation. So let's clear up some space now. So what we've figured out now is that to make a palindrome, you need every letter to have an even frequency, except at most one to have an odd frequency. So what we can do now is, instead of like grouping by letters, we really only care how many pairs of letters there are. So if there's like X, 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 Y, Y, we can just consider like how many pairs there are, because we don't care what the actual letter is, since it can just be appended to the beginning and the end. So we'll keep track of how many pairs we have, and yeah, so in this case, X has frequency 2, A has frequency 2, Y has frequency 2, so that's 3 pairs. And there are two odd ones out. Those letters are Z and B. So 3 pairs, 2 odd one out. So first of all, we're given K colors. Let's put all the pairs first, or at least most of the pairs. So what we can do is we can like find, so the number of pairs, there are K buckets here. Should have made that clear. K buckets. So number of pairs over 2 times K. What this gives us is the number of pairs we can put in each color, such that we want to level everything the same. So in this case, number of pairs is 3 over 2 times K is 0. So we can't put any sorry, number of pairs over, not number of pairs over 2 times K, number of pairs over K. So there are 3 pairs and there are 2 colors. So that gives us 1. So that means that we can only put 1 pair in each bucket of colors. And now we have 1 pair left and 2 odd ones left. So now we can treat the pair. Okay, so we know our answer, which is the minimum size of this, is at least 2. And we also know that it can't be 4, because if it was 4, then we would be able to put another like row of these. So our answer is either 2 or 3. And you might be wondering, like, why can't we just put 1, 4 and then fill out the rest with the odd ones out? But the problem is you can't put more than 2 odd ones out in one bucket, because then it's not possible to arrange the letters to become a palindrome. So yeah, we know our answer is at least 2 or 3 at this point. So what we can do is, for the remaining pair, we can split it into odd ones. So there's 1 pair, splitting it into odd ones, now we have 4 odd ones. And since 4 is greater than or equal to K, that means we can safely just add 1 to each like bucket, and our answer is at least 3. But we know it's not 4, so our answer is 3. So yeah, that was like with an example, but I guess I could explain like more generally. So we have K buckets for each color, and we have like some number of pairs and some odd ones out. So number of pairs over K, we can put that many pairs in each bucket. These buckets represent colors, remember. So that's an answer of at least 6. We know the answer can't be 8, because then we would be able to put 1 more layer, but that's not possible. So we took away K times what was it, k times 3 pairs, and for the rest of them we turn them all into odd ones out. So 2 times this plus odd, and if this is greater than or equal to k, then we can afford to put one odd one in each one. So then our answer is 7, and if it's not, then our answer is 6. So that's the gist of it. I know it took it was a bit complicated to explain, but I guess most of this problem was just thinking about it, and the actual coding this up doesn't takes 10, at most 10 lines, like 5 lines. It's really short. So problem E. This one I did not solve in the contest, but I think I have a solution now. E. Yeah, so we're given, you see these like phone numbers, and we're given like n phone numbers of size m, and we want to break this up into segments of length at least 2, such that these appear like somewhere in this matrix. So like 1, 2 appears here, 3, 4 appears here, 5, 6 appears here, 7, 8 appears here. Let's see what they come. So they took like 1, 4, the range 1 to 4 from the first phone number, the range 5 to 6 from the second phone number, and the range 3 to 4 from the third phone number. And that 1, 2, 3, 4, 5, 6, 7, 8. So we want to like make some partition like that. And each segment has to be length at least 2. So what we can do for this is we can use hashing actually. So first of all, what we'll do is for every single consecutive 2 digits, we'll see whether it appears somewhere in the whole phone number list. And we can do like, we can store a set of hash values, and of like what this number hashes to, what this number hashes to, 3 hashes to, 3, 4, 4, 0. So a set of hash values of length 2, and a set of hash values of length 3. So what 1, 2, 3 hashes to, 2, 3, 4. You could do this with the rolling hash, but it doesn't really matter since they're only size 2 and size 3. So if some, like, let's say what doesn't appear, if 4 or 5 doesn't appear, so if there's some 2 consecutive numbers that doesn't appear in this set 2, if like what 4 or 5 hashes to, that doesn't appear in the set, then we know that this can't be a segment and it has to be a split here. So like that, we can add splits between things that never show up. So see, 7, 8 shows up, 6, 7 shows up, 5, 6, or 6, 7 shows up, 5, 6 shows up. Okay, everything else shows up. So that's the only split we can make. So now our problem reduces to like separate subsegments. So here, what we can do for the rest is, if we have a segment of even size, then we can easily just break this up into segments of 2, because by definition of the segments, they must appear somewhere in these sets, in set 2. So if like the length is even, we can just break it all into sets of length 2, and it'll be there. We should probably make this a map to store actually where like the number occurs, 1, 2. And then, so the only problem becomes where there's a segment of odd length. 5, 6, 7, 8, 9. Let's say there's something like this. So now the problem is so there must be at least one segment that has 3 of length at least 3. So once we find that segment, we can just do the same thing as before, and we know these all occur, like the ones on each side of the triple, and we know those all occur in set 2 by definition. So yeah. So to find that segment of length 3 that appears, we can actually like literally just brute force. So we find 5, 6, 7, does it appear? If it does, we're done. Otherwise, we go on to 7, 8, 9, not 6, 7, 8. The reason we don't check 6, 7, 8 is because we don't want 5 to be on its own or 9 to be on its own. We have to skip every 2 so that the number of numbers on each side is even. So we check 7, 8, 9. Is it there? If it is, we're done. If it's not, then nothing has appeared and our answer is -1, because it's not possible to split that segment. So we can just repeat this for all the segments that we split here before, and then we'll have our answer. And if there's no answer, we'll just print -1. So yeah, that's problem E. And now problem F. I don't understand the title. Why did they just misspell it on purpose? I don't know, but whatever. So in this problem, we have a number x that is between 1 and n, inclusive, and we guess something, and we add some number to x. So x is initially something. We add some number to x, and let's say x plus c. We can choose what c is. So then x becomes x plus c, and then the system outputs the floor of x over n. And then we have to add again, and the system, and it keeps doing that, and we're only allowed to ask 10 times until we make a final guess of the current value of x, that is after adding a bunch of things. So yeah, since n is at most 1000 and we're only allowed 10 queries, that is like almost certain it's binary search of something. So yeah, binary search. And so what we can do is, we know that x initially starts from 0 to n. So the only way to get some information is, so the only differentiation is like if x is between 0 and n, or x is between n and 2n. So if we want to like sort of split this in half, if we add n over 2 to x, so x, okay, let me erase this. This is messy. Okay, so we add n over 2 to x. then let's say x was between 0 and n over 2. Then now the new x is between n over 2 and n, and the system will output 0. And if x was originally between n over 2 and n, then now the system, well, x will now between n and 3n over 2, and the system will output 1. So to like split this decision in half, we sort of like take the middle of 0 and n, what the original bounds for where x is, we take the middle and we set that to be n, and that splits the decision of whether x is in like a smaller range, which smaller range it is in. So here x equals x plus n over 2, so we can have like our initial bound L is 0, R is n. So if this outputs 1, then now we know R is 2n, or sorry. So if it's 1, then that means that x was between n over 2 and n. Adding n over 2 means x is between n and 3n over 2. So we can set L equal n, R equal 3n over 2. But if it was 0, or in other words, if the range, or if the value of the floor of x over n didn't change, then L is n over 2 and R is n. So in both of these cases, the length of the interval divided by 2. So we can just keep doing this process. So let's say we have current bounds L and R. We take the middle and we L plus R over 2, and we shift this over to the next multiple of n. And what that will do is that will just make L and R equally spaced about a whole number, meaning that there's a half chance that it'll be in a smaller interval and a half chance that it'll be in the other interval, and we can detect that. So that's it. That's the problem. I thought it was pretty clean. And then problem G, min or tree. So we're given a graph and it's a simple problem. We just want to find the minimum spanning tree, or the spanning tree with the minimum OR of all edges. So in this case, it would just be one, just like this edge and this edge, because then their OR is 2. Because if we did this tree, then their OR would be 3, and that's too big. Okay, so how do we do this? The first thing, I guess, to notice is that it's most important to, or okay, so if none of the edges use a we can decompose this into powers of 2. I guess that's probably easiest. So this is 2 to the 1, 2 to the 1, 2 to the 0. If we had like an edge of length 3 is 2 to the 1 plus 2 to the 0, etc. So what we do is we initially have like an array that says, do we use this power of 2? So this array is size length 30. So initially everything is set to 1. So this sort of represents the number that this represents like the actual OR value, the answer. So if everything is on, so these values are like 1 or 0. If everything is 1, then that means that we're allowed to use everything, that is. So like let's say this is 0. That means we're not allowed to use 2 to the 0, because if we were to use some edge that has 2 to the 0 in its decomposition, then the OR of all the edges would include that, and this would be 1, which is not what we want. So that's why this represents like the OR of everything in the spanning tree. So what we're going to do is sort of loop from 2 to the 30 or like whatever, and we're going to loop from like the highest place value to the lowest place value and see whether or not we're allowed to use that. So we start off at like 2 to the 30. Are we allowed to not use 2 to the 30? That means that like if we were to take out every edge that has 2 to the 30 in its decomposition, then would there still be a spanning tree? And of course here the answer is yes. But the way to check that is we loop through every single edge. If it contains a 2 to the 30, if it doesn't contain a 2 to the 30, we union them in a union find data structure. So all we're trying to see is whether the graph is connected if we don't use 2 to the 30. And of course it is in this case, since none of them have 2 to the 30. And since it's connected, that means that there exists a spanning tree, and its OR value will be, like, there exists a smaller OR value. So this can be 0. Similarly, 2 to 29 can be 0. And we keep doing this. And let's say we reach something like 2 to the 4. And removing all the edges that have 2 to the 4 in it, along with like everything, we're removing all the edges that have like some power that has a 0 in this array. So like we already removed everything with 5 to 30, and now we remove everything that has a 4 in it, 2 to the 4. So let's say it becomes disconnected in this case. That means there is no spanning tree with all those removed, and this has to remain 1. And what we do is we just keep going. We test 3, and if it's still connected, and remember, when we test things that are smaller, we look at this array, and if an edge contains 2 to the 4, that's fine, because its value is 1. But if it contains 2 to the 5, we don't union them. So in that way, we can just like loop through everything. And once we're done, this value will just be our answer in binary. And we can just like compute like the answer. And like the reason this works is because we're going from highest place value to lowest place value. Like the only thing that matters at a given place value is whether that can be 0 or it can't, because nothing that comes after this place value can supersede the importance of this, since that's like the definition of place value. So yeah, that's why this works. And yeah, that's it for problem G. I thought it was pretty clean. And yeah, I think that's it for the video. So I didn't label this problem G. Better late than never. But yeah, thank you for watching, and I hope this was helpful.